Welcome to the third lecture in Introduction to the Lattice Boltzmann methods. We are still in the theory of the Boltzmann equation itself. So today what we are going to do is to derive the Navier Stokes equation from the BGK, Boltzmann BGK equation. So the title of today is Hydrodynamic Limit of the BGK equation. And this, now let us start, of course, with the BGK equation itself, which was derived in the last lecture. BGK equation, which we this time write without forces, without macroscopic forces like gravity, far field forces. So this is the time derivative of the distribution function plus the advection term. This is equal, so this part is from the Boltzmann equation itself, and the BGK equation is the simplification of the collision operator as the difference between an equilibrium state coming from the ether theorem minus the state in which the particles are divided by tau. So what is this tau? Tau is the time scale for the return to equilibrium. So I say return, implying that the particle has been in equilibrium before. Now our assumption is when the particle last time collided, it forgot its memory, and by forgetting its memory, so forgetting its memory means everything that is not conserved is deleted from the history of the particle, and then it is drawn, the particle speed is drawn from equilibrium. So when particles collide, what happens is they lose their memory. So memory means we can no longer tell from their outgoing direction what their ingoing direction was, expect from of course the energy and the momentum that particles in this area would usually have. So there would be an offset, but otherwise this distribution is drawn from the equilibrium. So let's consider the following. We have here, say, a collision. So here is the last time the particle collided. Then it's moving. And here's another particle. Here was another collision. And another particle going here. And they collide again. So the important thing is that particles collide repeatedly, and what we need to understand, or what we need to know, is the distance, lambda, that a particle travels between two collisions. Well, in this distance lambda is equal to some velocity c times the time that it takes from flying to say A to B. So this lambda, this is what we call the mean free path. So it's, of course, the mean between two collisions. So because of course, not all particles fly the same distance between collisions. So this is why it's the mean. So, and this is the mean free path in brackets between collisions. Usually we just say mean free path, which means the path traveled between two subsequent collisions. And then tau is what we call the mean free time. So, and C would be the mean magnitude of particle velocity. So it's important that it is the magnitude, because when you regard gas at rest, then the mean particle velocity would of course be 0. But this is not what we mean. We mean the mean of the velocity, and the mean of the velocity is of course not 0. It is more related to the speed of sound up. So it's proportional to the speed of sound up to a constant of order 1. And the particle speed after the collision c after the collision this takes on, this is also, better say, this is drawn like a random number. It's drawn from equilibrium. This is drawn from equilibrium, so it means that this particle just happens to take on any potential velocity, with the probability given by the equilibrium distribution function. So, and now this tau, as has been indicated here, this tau is now proportional to lambda divided by Cs, where Cs is proportional, is related to the speed of sound by to the thermal speed. So the magnitude of the particle's velocity c by a constant of order 1. Okay, so this is the mean free path. Now the next topic is the dimensionless numbers that are usually used to describe kinetic theory, and they should be well known from the so-called Buckingham. Or pi theorem. So this is the same thing. Buckingham was the guy and pi is the generic name for this. So we know from the theorem that natural systems can be described by non-dimensional numbers. Some of them you have already heard and some of them probably not. So a physical system is usually described by things that have units. So we can describe it by dimensional numbers first. So this is natural. So for example, the velocity u gives us velocity scale. So we will usually use units, and this would mean this would, for example, be 1 meter per second. Then we would have a system scale called L. That would be, for example, 1 meter. Now, to give you an idea, let's see what we have here is a domain size, and we are looking at something physical, for example, a car. This is usually what Lattice Boltzmann is used for. And this car has a length L, and it travels by a velocity u. Okay, now this describes our system with units, and now we want to describe the system without units. Then there are two dimensionless numbers that we have to take into account. So now the dimensionless numbers. Is the first one being the Knudsen number being the mean free path. So this is this very microscopic thing. So when you have a collision here and we have the next collision here, then this would be lambda, obviously not drawn to scale here. This lambda divided by L, this is called the Knudsen number. So this is probably one that you have not yet heard, but you would have heard about the so-called Mach number. The Mach number is the velocity of the object, so the characteristic velocity in the system divided by the speed of sound, and this is called the Mach number. Okay, now we can write our other parameters, our parameter lambda, which of course is a dimensional parameter. We can write this as Knudsen number times the length of the system, and Cs is u divided by the Mach number. And tau, because it is lambda divided by Cs, or proportional to lambda divided by Cs, we'll find that this is Knudsen times Mach times L divided by U. So it is sometimes found useful to express these small dimensional variables, which are usually too small to measure, in terms of the macroscopic variables and these dimensionless numbers. Okay, now the point of today's lecture is to see how this kinetic picture relates to the continuous picture, and this is observed by looking at limiting cases. So, what happens in continuum if we want to consider our system in continuum? So we know there is no continuum. In reality, we have molecules, yeah? We have a mean-free path. So what happens in continuum is, or when is the continuum assumption appropriate? It is appropriate if the system is much larger than the mean-free path. And if this is the case, obviously the Knudsen number goes to 0. Another limit that we are looking for is that the flow is slow. Slow means that the characteristic velocity of the object in the flow, or the flow itself, that would be the same, this is much, much smaller than the speed of sound, which means that the Mach number is going to 0 too. And by the way, this one here is called the incompressible limit. Okay. So these are the assumptions under which we expect that we get to an incompressible continuum limit. So this is the next topic, the incompressible continuum limit of the BGK equation. So, and we do this by the use of the countable raw moments that we have introduced already last time. So using raw countable moments. So first, let us again write our BGK equation. This is the time derivative of f plus the advection term equal to the BGK collision operator. So, and now we have to be very precise because we go through all the steps. Now I have to introduce you to how we write this advection operator. So we have basically a vector with the components xi, upsilon, and zeta. This is multiplied into dx, dy, and dz. So this is this operator here. which means that we can write our BGK equation if we write it in, if we expand it, then it will look like this. So we have xi times dx of f plus epsilon dy of f plus theta dz of f equal to the collision operator. Okay, so far so good. Now comes the, again, the definition of these countable Ra moments. So they are required here because we have to transform this equation from the variable f, which is the particle distribution function, which is the probability density of finding a single particle in a specific state. This we want to turn into macroscopic variables. Macroscopic variables are moments. So this moment is MABC. Sorry for this disturbance. This is MABC, defined from the integral from minus infinity to infinity, f xi by the power of a, epsilon by the power of b, and theta by the power of c, and this integrated in three-dimensional velocity space. So this is a moment of the distribution function f. And now we can not only take moments of the distribution function f, but we can actually take moments of the BGK equation itself, where we simply put the entire equation in the place where here is the distribution function. Okay? So this gives us two moments of the BGK equation. Now this looks like this. We take the integral over the left hand side of the BGK equation from minus infinity to plus infinity, xi a epsilon b theta by the power of c, and this into dt f plus dx xi. So what I'm currently doing here, you remember that xi was actually in front of the differential operator, but because xi here is not dependent on f, what we can do is we can put it inside this derivative, dy epsilon f plus dz theta f, and this we have to integrate over the entire velocity space. And now comes the right-hand side of the BGK equation, which is xi by the power of a, epsilon by the power of b, and theta by the power of c. This goes into f eq minus f divided by tau, and this integrated over the entire velocity space, xi. So what we now observe is that all terms are linear, and xi, epsilon, and theta not dependent on x, y, c. which means because they are not dependent on x by c, it doesn't matter whether they are in front of the operator, and they're also not dependent on t, by the way, because they are independent on the guys where we take the derivatives. It does not matter whether they stand in front or inside. So what we can do is we can put these guys also inside, which we now find useful, in particular by seeing that so we can put this inside, and we can also distribute the integral over all the different terms of f, then seeing that we get an equation in terms of the moments of f. Now this will look like this. So we put, for example, we start with this guy here, with the time derivative of f. We put these xi by the power of a, epsilon by the power of b, zeta by the power of c to the f, and put the integral also on the f, which gives us the moment m, a, b, c. So the same thing can be done now for this guy, where we collect xi by the power of a, epsilon by the power of b, and zeta by the power of c into this guy here in front of dx, and take the integral. Now what we have here is another xi, which means we have to integrate over xi by the power of a plus 1, which means that in this here we have m, a now plus 1, b and c. So this goes on with this guy, where we have one epsilon left, in addition to the ones that we have here. So we have in the next term dy m, a, b plus 1 and c. And for the last term on the left-hand side, we have an additional zeta. So we'll have d z m, a, b, c plus 1. And the same thing on the right-hand side, where, of course, we have only these guys. So we'll have the moment m, a, b, c, the equilibrium thereof, m minus m, a, b, c, and this divided by tau. So now this is the equation in terms of moments. Okay, now we see that there is now moments, that the time derivative of one moment depends on the spatial derivatives of other moments, by the way, moments of higher order. And this is what we call the hierarchy of the moment equations. So we can look at this starting of course with now specific values for A, B, C. So A, B, C are the counters of this moment, and of course we start at the beginning, and the beginning is that A is equal to 0, B is equal to 0, and C is equal to 0. So what is this? This means this is M 0, 0, 0 is just the integral where we have xi by the power of 0, upsilon by the power of 0, and theta by the power of 0, which of course altogether is 1. We can actually skip this. Integral over f dxi, and this is the particle density. In the first lecture I said mass, but it's actually the density. So this means we get this equation here would be an equation on the evolution, the time evolution of density. Now you see so what you observe is we count the indices according to their direction in space. We always count one index up. So the time derivative of this 0 moment comes plus the spatial derivative in x with the velocity in x direction, one counted up. The derivative in y with m0, 1, 0, so the y velocity, and dz, of course, with the z velocity, and this will now be equal to m0, 0, 0 equilibrium minus m0, 0, 0 divided by tau. Okay, now we have to know what is this guy here, and this guy m100 is of course the integral from minus infinity to infinity, f now multiplied by xi to the power of 1, the others are power 0, therefore they do not appear, and this integrated over all the three different velocity directions, and this gives us the density times the macroscopic, so the average velocity in x direction. So this is not the particle velocity, but this is the average velocity of the particles of the particle distribution function. So this is the macroscopic velocity that we observe if we regard the fluid as a continuum. So, and of course, the other guys are the same, just in different directions. So this here, m010 is the y velocity, and m001 is the z velocity. Okay, what else? We just recognized that m00 is the particle density, so in number of particles per square meter, and this is something that is conserved during the collision. When it's conserved during the collision, it means that the equilibrium must be equal to the state in which it enters the collision. And this, of course, means that in this particular case, the right-hand side of the equation needs to be 0. Okay, so this means we can now write the entire equation in this format: dt rho plus dx rho ux plus dy rho uy plus dz rho uz is equal to 0. And this can be rewritten again as dt rho plus divergence of rho vector u equal to 0. And this is something well known from continuity. Actually, this is what the name continuity is coming from, is the continuity equation. Okay, so what it says is that the density changes with the divergence of the flux of particles. So u times rho is the flux, and if there's a divergence of the flux, then the density changes. Otherwise, it does not, because the number of particles is conserved. Okay, so this was the first equation. Let's look at the second equation. This is by taking A equal to 1, B equal to 0, and C equal to 0. And we'll only look at this case because of symmetry reasons. The case A equal to 0, B equal to 1, and C equal to 0 would, of course, be exactly the same, just in a different direction. So we only need to look at one of them. Okay, so what we have then is dt m100 plus dx. Now again, we count up the moments. So we had here m100. We have to count up the first index by 1. So this gives us an m200. Now next we have to count up the second index by 1. This gives us a 110. Plus we have to count up the last index by 1. So this is 101. And this again is equal to m100 equilibrium minus m100, and this divided by tau. Okay, so again, as before, this guy is 0 because m100 is equal to rho ux, and this is the velocity times the density. So if you add the particle mass to it, then it will be the momentum, and this is conserved. And because it is conserved, means that the equilibrium of this guy is equal to the state at which it enters the collision. Okay, now this is 0, but what we need now is to proceed is to know what is actually this, and this. And so we start with M200. What is this? Well, we can calculate it from A equal to 2, B equal to 0, and C equal to 0. This will give us dt m200 plus dx. Now we have to count up the first index again. From 2, 1 more is 3. dy, now we have to count up the second index with 2, 1, 0. And last we have to count up the third index, 2, 0, 1. And this is equal to m200 equilibrium minus m200, and this divided by tau. So now M200, we learned last time that this is related to energy, so we could assume that this is conserved. However, actually, this is not the case. M200 is not conserved. Because what is conserved is M200 plus M020 plus M002. This is the energy. This is the energy, and this guy is conserved. So what is conserved is the sum of these three moments, but this doesn't mean that the moments are individually conserved. So we cannot assume conservation of any of these moments by themselves. So now what we want to have, we have this equation for M200. What we actually want to have is this moment itself, and what we now do is we invert this entire equation to get this M200. So this basically looks like this. So we take the tau on the other side and then the equilibrium also on the other side, and then we get M200 is equal to M200 equilibrium minus tau, and then what before was the left-hand side, so we'll end up in dt, M200 plus dx, M300 plus dy, M210 plus dz, M201. Okay? Now everything here will be the same for the other moments. So because the calculation is exactly the same, I'm not going to repeat it here. We just get in a similar way M110 would then be M110 equilibrium. So again, we get the equation, we solve the equation for M110, assuming that the collision operator in this case is not zero because it's not a conserved moment. So look exactly the same. This is the equilibrium minus tau. And now comes the left-hand side of this equation, where again we have the moment itself, and then we have the moment, the spatial derivative in x, with the first index counted up by 1, then the spatial derivative in y with the second index counted up by 1, plus the derivative in z with the third index counted up by 1. So it just looks like this, and then the only other one that we need, and this of course is now simply an exchange of indices. So this one is also M101, is also in the equation that we were looking for. So it's minus tau dt M100, the moment itself, dx M201 plus dy M111 plus dz M102. Okay. Okay, so What we need to know to get forward is, of course, now these equilibria here, and they can be computed from the equilibrium distribution function, of course. So the equilibrium for m to 0, 0 is the integral from minus infinity to infinity. Now comes rho 2 pi k Boltzmann constants divided by the mass of a particle. So I remind again, this rho here is not the mass density, but is a particle density. So it's not kilograms divided by cubic meter, but it's 1 divided by cubic meter. Yeah. So you will find the same equation with another definition, and then and the mass will be included in the rho. Okay, so this by the power of 3/2, and this then again multiplied by the e by the power of xi minus u, all of this square times the mass divided by 2 kBt. And now this has to be integrated, because it's a second moment, it has to be integrated over xi square, and multiplied by xi square, and then integrated over the entire velocity space, so with the vector velocity space. And if you do this in Mathematica, unfortunately you have to wait for 5 minutes, but at the end you get this result that it's related to the temperature. So basically an energy part, or temporal, and here we have kinetic parts, so kinetic energy, so temperature, thermal energy, and kinetic energy. Okay, so for the moment M110 equilibrium, this would be the integral from infinity, from minus infinity to infinity, starting from the same equilibrium distribution function, xi minus velocity of the fluid times m times kb 2 kbt. Now this has to be integrated because it's in 1 and 1, so we go over xi and over epsilon, and we integrate this over all 3 velocity directions. And now what comes out is u is the particle density times ux times uy. And similarly, okay, I'm going to write it down anyway. For the last one, M101 equilibrium minus infinity to infinity rho 2 pi kb durch m by m, this to the power of 3/2 e by the power of, oh God, I forgot the minus everywhere. Okay, minus xi u square m divided by kbt. Now this has to be integrated over the kernel xi, x velocity, and theta, epsilon velocity, and now integrated over the entire velocity space. And as you could imagine, this gives rho ux uy, just by symmetry. Okay, now we got the first part, which is the equilibrium. The next thing is the next thing is we have to deal with these guys back here. And you see there are again new moments, and this will now go on here forever. And in order to stop this here, we make an assumption by reminding us again what is tau. So tau is Mach times Knudsen times L divided by U. And let's say that our system is very large. As we would usually do if we go from molecules to a continuum. So the continuum compared to molecules is very large. So we assume that the Knudsen number is 0, and by this we'll assume that tau is also equal to 0. So as tau is equal to 0, then in our equation up there, the entire part that comes here would be 0 because we multiply this by 0. And the second order moments, M101, M110, and M200, they would all just be their equilibrium, okay? So under this assumption, what we get is dt M100 plus dx M200 equilibrium plus dy M110 equilibrium plus dz M101 equilibrium is equal to 0. Okay, now let us take the equilibria that we just computed and put them into our equation. So this is dt goes on rho ux, which is this guy, plus, okay, now comes this guy. This guy is dx rho k Boltzmann divided by mt plus ux square rho. This is what we just derived. Then next guy, this one, plus dy on ux uy rho. And last one, this one, dz ux uy rho, and this is equal to 0. So what we generally observe here is that there are multiple nonlinear terms. So we get the velocity, we got the product of two velocities and the density, for example. Okay, so this we now rewrite by applying the differential operators first to one of the velocities. Yeah, for example, this guy here, we apply it first to the velocity and take the rho out. And this is a chain rule. Yeah, so we have ux. No, I do it the other way around, sorry. So we take ux in front and have dt rho, which means we still have left, we have to keep in mind that we also have rho times dt ux from the from the chain rule, but this we keep in mind. I will write this later. First, we'll proceed with this guy here. So this guy will give us ux dx rho ux. So say we've touched that one. Now we've touched that one. We skipped over this one. So we have to keep this in mind. So we go to plus ux. So we are now here. Plus ux dy, this was an x, dy uy rho plus ux, the last one here, dz uz rho. So I did this such that we have ux in front of all the operators. But now I left out some of these parts, and these parts that I left out, they I have to add. So as I said, now applying the chain rule to this one, taking into consideration the part that we took already here, gives us rho dt ux plus, now the next part of this guy gives us rho ux dx ux plus the missing part of this guy is uy rho dy ux, and still the missing part of this guy plus uz rho dz uz. Sorry, this must be ux. Okay, by the way, this must be a set, obviously. Otherwise it doesn't make sense. So now, do we have everything? No, we are still short of this guy here. And what I'm doing with this guy here, I put it on the right-hand side of the equation. So then I have to write a minus. Sorry, I was referring to this guy. So I have to write a minus and have minus dx rho k Boltzmann m and t. Okay, now this is my new equation, and I put this into this particular bracket so that we can distinguish this part that I put in brackets like this, because I can rewrite this as equal to ux times dt rho, and the rest would be the divergence of rho times u, and this we know already as the continuity equation, which when we have particle conservation is 0, so this entire thing here is 0. Yeah? So we can get basically rid of this entire guy, and we are only left with the remainder. And this remainder can also be rewritten in a little bit more beautiful form as rho times dtux plus rho u plus u times nabla u. So what you observe here is that we have ux times dx on ux. We have uy on dy on ux, and we have uz on z, dz also on ux. So this will give us vector u, scalar product on nabla, and this applied to ux. And this is equal to minus dx rho k Boltzmann divided by m and t. So do we know this equation? Probably yes. So the question is, what actually is this guy here? So this guy here comes from the so-called equation of state, and we'll take the equation of state of an ideal gas, perfect gas, law here, which is the pressure times the volume is equal to K Boltzmann and T, and the volume is equal to 1 over the density, which means that we can write this as P is equal, so the pressure is equal to rho K Boltzmann and T. And if we put this into the above equation, we get to rho times dt u plus ux, rho u, so the advection operator on u is equal to minus, so we have here still the particle, a mass. This is here because our density that we are using is the particle density. So we have to scale this by 1 over m dx into p. And this can, of course, also be done the same way for uy and uz, and then it is called the Euler equation. So this Euler equation drops out of the Boltzmann equation under the assumption that tau is equal to 0. Now the problem, of course, is that in reality tau is never equal to 0. And now we have to look at what actually happens with the case when tau is different from 0. So when tau is different from 0, we get a different equation, which looks a little bit uglier. Then we start, of course, for starter, we have the same thing. So everything that's inside the Euler equation we still have. But then on top of the Euler equation, we have the part of the previous equations that comes with the tau, and they have, of course, different parts for the different moments. So for example, so we start with tau times dx, and now comes these equations for the moment m200. This goes with dx m300 plus dy m210 plus dz m201. Then comes the remainder of the parts related to m110 is dx m210 plus dy m120 plus dz m111 plus tau dz into dt m101 plus dx m111 not 1, 2, 0, 1, plus dy m1, 1, 1, plus dz m1, 0, 2. Okay, now this is bulky. Because it's bulky, what I'm going to do is I call this sum here, which distinguishes the Euler equation from this new equation. I call this guy S. And we see this contains a lot of third order moments. So where do we get the third order moments? Well, again, the same way, we have to get the equations of these third order moments, and this leads us to the so-called closure problem. So there's so-called closure problem. In order to get the equations of the third order moments, we need the next order of moments. And there is more to it, so dot, 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 yeah. You get the next order of moments, M300, so this now works exactly the same as we had it before. M300 is non-conserved moment, so this is equal to the equilibrium minus tau dt M300 plus dx m. Now we have to count up the moments. Now we get M400, and here you already see the problem. Namely, we get again the next higher order, so these are moments of order 4. We also have moments like this here. M210 is M210 equilibrium minus tau dt M210 plus dx M310 plus dy M220 plus dz M122. Yeah, and then we have to compute the one M111, and okay, now you should actually have gotten it, so this you can do as a homework, because you just have to count up the moments. So now you hopefully understand that you have these equations which depend on yet higher moments, and in order to calculate these yet higher moments, you still the moments at the next order, which would be the fifth order, and this will go on forever. So here we know for which we need the next order of moments. Okay, so this goes on forever. This will never stop. Yeah, we get an infinite hierarchy. So apparently the case is completely hopeless. Yeah, so there's infinite information in it. But we've already managed to stop this in the previous order and got the Euler equation. The question is, can we stop it again? So how to stop this? At any further order. Okay. Now we said, previously we said tau is supposed to be small, and we got the Euler equation by saying it is actually 0. Now the assumption is a little bit weaker. We say that tau is small, but not 0. So, and this we indicate by tau, by saying that tau is larger than 0, while tau square is going to 0. Yeah, so if tau is very small, but it's larger than 0, then we have to take tau into account, but we can ignore tau square. And this is important because we noticed before that all this, the non-equilibrium second order moments, which we talked about before, are multiplied with tau. And the non-equilibrium part of the second order moments is composed with the equilibrium of the third order moments and tau times the derivatives of the fourth order moment. So in the final equation, the equilibria of the third order moments come together with tau by the power of 1, while this here will become a tau by the power of 2, because the entire thing comes with tau in front and is multiplied with another tau. So this means if we assume tau square equal to 0, then in the final equation, everything here will be gone. So this is the assumption that we take now in order to actually get an equation. For this, of course, now we have to derive the equations for M300, for example, which now, as I said, is M300 equilibrium plus something of order tau. And this again is, of course, now the integral minus infinity to infinity rho. Now comes the distribution function 2 pi k Boltzmann t divided by m to the power of 3/2 e by minus xi minus u, the entire thing squared, times m divided by 2k Boltzmann constant t, and this now integrated over the kernel xi to the power of 3, integrated over the entire velocity space, and then there would be this order tau thing left, and what we are receiving is rho ux 3k Boltzmann t divided by m plus ux square, and of course this guy that later we can ignore. So similarly, without writing the details now, m to 0, if you take this integral, you will have uy rho k Boltzmann t divided by m plus ux square. So we notice we get something related to temperature, together with the velocity. So this seems to be looking like some advective flux of velocity plus something related to a velocity to the power of 3. And now we also have M111 equilibrium equals to rho ux u y u z. Okay, now this we can put into our equation and derive the Navier Stokes equation. Unfortunately, unless you had the feeling that this is complicated, I have to inform you that from here on it gets pretty complicated. So it's not impossible to go on with this equation here. We'll see that many parts drop out, but we now simplify our life by making a few assumptions that are not necessary, but they are useful in order to actually get to an equation before the time for the lecture is over. So one thing that is actually important to assume when we already assume that tau square is equal to 0, if we just already assume this, then we better also assume that temperature is constant, because otherwise we run into inconsistency. Yeah, so for temperature not to be constant, we would have to consider the tau square parts, which we already ignored. So now we assume temperature is constant, and we also assume, this is not necessary, we also assume that velocity is small. Low velocity means that the terms ux cube and the other terms like for example ux, y cube and so on, they are assumed to be 0. Because otherwise the equations will get very, very large. And with these assumptions we can simplify the thing that we called S before in the following way. So we get, again, this depends on tau dx dt k Boltzmann t m rho plus dx 3 ux k Boltzmann t divided by m and rho plus dy u y k Boltzmann t divided by m plus dz u z k Boltzmann t rho divided by m, and this first part we're going to call as x. So what I've skipped here is that inside this, because we only took the equilibrium, comes a term O tau, and this O tau here, coming from the non-equilibrium of the third order moments, is multiplied with this tau here, giving us a term of the order of tau square. And because we said we are going to ignore terms of order tau square, we do no longer need to write them, and I will skip the terms completely in what follows. So here we have another term, tau dy dx u y k Boltzmann t rho divided by m plus dy ux k Boltzmann t divided by m and rho, and that's it for this moment. because there should also be a time derivative of the moment, but in this time derivative we have the velocity to the third order, and this velocity to the third order we said is assumed to be 0, and then there is the then there would be a spatial derivative of the m111 moment, but since we're assuming that velocities cube are 0, this entire moment will also be gone. So in this, here we call this the SY, and then there's a last term that is tau dz dx u z k Boltzmann t divided by m and rho plus dz ux k Boltzmann t divided by m and rho, and this is our S set. Okay, now here again we are recalling the continuity equation, which was in this case there is a continuity part inside this this term here up here, because we see we get the spatial derivative of dx ux, dy uy, and dz uz. Yeah. The only thing that we have to take into consideration is that we actually get the first one 3 times. So we have to take we can eliminate, or we can combine one of the 3 ux's here together with the other guys here and draw them out to see that this is something that's going to disappear, because in the first line, so in Sx we have the spatial derivative in x direction of k Boltzmann t, which we assumed is constant, therefore we can draw it in front, dt rho plus the divergence of rho u, and this is something that this guy here is what we know to be 0, so the entire thing is 0, and therefore we can write Sx simply as tau dx on tau dxx, so dxx is how I write the second derivative of what is left, 2 times ux k Boltzmann divided by m times t and rho. So now with this we can write the entire S part like this. We put tau in front, and now I isolate different parts. So what I want to have is I want to have the derivative that goes in the second derivatives that goes in x, x, y, y, and in z, z direction separately. So I take the half of this. We'll soon understand why I take the half of this. Maybe I write, okay, in order to simplify, I take KB and KBT rho, no, rho, not rho, KBT by M. I take this in front, to the front, and still have left dxx ux rho. So this is half of this, plus I take the yy ux rho, which is coming from the sy term. So this is this thing together with this derivative here, plus I take dzzz ux rho, which is this term. Okay, now I have to add everything that is still missing, and the first thing is missing is this guy, because we took only half of it. So now we have to add the other half, tau k Boltzmann t divided by m. So the other half of it is of course the same thing, dxx ux and rho. And now we have to take the guys, this guy and this guy, who were previously missing from what we wrote. So we get dxy uy rho plus dxz uz rho. Okay, you probably noticed that I, especially here, I exchanged the order of the derivatives, which is here no problem to do. Okay, now this is our S, and this S can be now rewritten. Yes, S can now be rewritten in terms tau k Boltzmann t divided by m. So because I've gathered all the second derivatives here, what we observe is that this is derivatives of the same thing. It's always the velocity in u in these three different directions. This we identify as the Laplace operator applied to the velocity ux. And the other part, we identify that there is a dx everywhere in front, and otherwise it is dx ux, dy uy, and dz uz. So this can be restated as tau k Boltzmann t divided by m dx, and comes the divergence of u. Okay, and now this can be combined. This can be combined with the previous Euler equation. So we have again the time derivative, the change in time, times the advection operator on ux is equal to minus dx the pressure plus tau kb by m and t, and this goes into Laplace of ux and rho plus dx the divergence of the velocity times rho. And this here, this guy here is what we identify as the viscosity. And if this is the viscosity, then this entire equation is the incompressible Navier Stokes equation, which we now have derived from kinetic theory. So, thank you for listening.